Hi, in this video on my Arduino Mega2560 I want to continue where I left last time, which is measuring the value of the NTC, and with result that I didn't expect, because the value of the resistance meter showed about 100 ohms, while the value of the NTC was quite different in the serial monitor. And when I point the camera on the multimeter, again set to ohms, it is actually just with these clamps, and when I touch them it goes to 0, and this way it gives maximum resistance. So with the camera back to the NTC and I connect him, and now I have to take care not to touch any other wires. They are not making contact, and the indicator shows exactly the same, if not higher, which basically means that there's that the NTC is not conducting anything. So my assumption from last time was wrong, and there has to be some different explanation for this. Now, while watching the NTC, it says 29 to 30 in the serial monitor, which is clearly not the same as the indicator of the multimeter shows. So I have to investigate more about that. So let's do that first. After doing some research on the NTC, which is an 1K5 resistor. 1K5 is actually 1500 ohms, and as already known, it is a negative temperature coefficient. However, this does not explain the behavior of the multimeter. It does also not explain these values, because considering the 1500 ohms, this makes no sense. And when thinking about the temperature, it makes no sense either, because it can't be up to say 40 degrees, measured in Celsius of course. Fahrenheit doesn't make sense either, but it's a European product, so that will be Celsius. So these values make no sense to me, and then I find the Steinhart-Hart conversion formula, and for that formula to use, you have to know much more about the NTC. So I think that my idea of measuring the NTC is a no-go for now, although the idea was nice with the motor and the lamp. But I will relay my focus to another thing, and that will be extending the circuit with electronics, like I have now the RLC circuit, resistor, inductor, capacitor, and I will see if I can do some more with it, like I intended in the beginning, with seeing how an LED would respond to it. So that is what I'm going to do next. And for that I can also use the Scilab XCOS simulation. Before going to another simulation, I thought it would be interesting to see what happens when I put this lamp in parallel to this LED, since we thought that without it the LED is bright and slowly dims, and then I short circuit the capacitor and it goes on and on. So what happens if I put a lamp in parallel and okay, it's in parallel, I short circuit the capacitor and nothing happens. The LED doesn't brighten up. So could it be that with the voltmeter is not bright enough, or without the motor attached it's hard to notice, but now all the lights are burning fully, and a short circuit and nothing happens, while I disconnect it and there it goes, very bright and slowly dimming. So this lamp is not good to put parallel to an LED, which is too bad, because in that way I could have a nice setup with the NTC. Anyway, it is not meant to be, apparently, so let's go to another simulation with the resistor, inductor and capacitor. So what I actually want to do is put another series of inductor and capacitor next to it, and for that I will take an LED from an earlier used circuit on the breadboard, and I have several possibilities. I can put a resistor here, so let's do that. A resistor, rotate, and then another inductor, add another capacitor. And because they are, there will be a different capacitor and a different inductor, I'm curious what the end result will be in terms of voltage. So I need one diode, nope. This is not going as I intend. Slightly better. Then I need a voltage sensor. Let me put it here. Then I need a sink. Scope is a nice one, and I need the clock, which is a source. This one goes here, a little bit down, that way, and now all I have to do, not all I have to do, because I have to put connect it to the ground. Ouch. Not quite nice. This is better. Bring it down a little bit, and then I have to connect it to there. And that's it. Now I have a block parameter to choose to use, and for some reason it doesn't do that. Away. Because in this way I get probably two different values, and let me just take one other capacitor, see what value that is, and this is, let me take this one as an example. So the new one should be 0.0022. And the initial voltage is 5, so I have to put it at 5 as well. Or is that the whole thing, that if I put it to 0, let me put it, let's just hold it this way. 1, and let me put the other one to 1 as well. I think this is fair. This one is 220. The other one is 220 as well. It's exactly the same one. (220 ohms). And now I'm very curious what will happen. Let me first save it, because this is a different one, version 2. And run it. See what happens. And you can see that this one is going down faster than this one. So I take it that this one is this smaller capacitor, since this one is 6800 and this one is 2200. So the smaller one will go down faster. That is in simulation. So this is quite nice to see the difference. Here it is around 8 and here it is already at 5. And the whole difference is a capacitor of a lot less farad, microfarad actually. So with this I can build a parallel circuit and see what happens in reality. So with the other RLC circuit with an LED put in, I can adjust the voltage, or anyway, let's see, this is nicely done. However, this one is much quicker done than the other one, just like the simulation showed. This takes a while, and this is very much quicker done, which again is like in the simulation. So with this new setup working, all I can say now is thank you for watching. Too bad that the NTC experiment didn't work out as I expected. But those are experiments. Sometimes it works, sometimes it doesn't work, and other times it does. But certainly these experiments are to be continued.